Hello everyone. Today we're going to introduce you the applications of hydraulic libraries. Our learning objectives are to get familiar with applications of different hydraulic libraries by showing some examples of typical hydraulic system models. Besides, you will also know what can be obtained from a hydraulic model. We will present some real MSIM models of hydraulic system and their results. In the following slides, we will show some examples of hydraulic system model and hydraulic component models. In this slide, you can see a typical application on engine fuel injection system and its component. In the middle, it's a cross-sectional view of a diesel injector, which is widely used in different kinds of diesel engine in automotive, construction machinery, and shipbuilding industry. On the right-hand side is a HCD component model representing this diesel fuel injector. You can see from top to bottom, there is a solenoid component, spherical poppet valve, then in the middle, it's a control piston and needle, and at bottom, it is the nozzle of the injector, where the fuel will spray into engine cylinder. With this detailed injector model, the simulation engineer can perform different analyses to check how design parameters such as orifice diameter, spring rate, and preload could affect the injection duration, injection rate, and so on. Okay, let's check the simulation results of this common rail solenoid injector. So you see here, it is the solenoid input signal, which is imposed at this component. And we can also see the calculation results of the control valve lift, needle lift, and also this important physical variable, introduction rate and injected mass. And we can clearly see that there will be some time delay between the command and also the responses, which is also an important criteria for this kind of system. In this slide is a swash plate pump model created with hydraulic component design library. You can see the mapping between schematic and MSIM model. For example, the control valve is modeled with HCD component such as simple piston and spool with groove. Also, the return spring and spool is considered by using mechanical components. Based on this detailed pump model, the designer can perform sensitivity analysis to find out which design parameters will have impact on system performance. It's also possible to create 3D animation to visualize the pump working. Now let's look at the real swash plate pump model in SimCenter MSIM. It's a simple and short scenario. Let's check the results. So at the beginning, the swash plate angle is at around 5 or 6 degrees, and then when the swash plate is going to its vertical position, so that's basically 0 or 1 degree, and we can see the flow rate, which is providing from this pump, is varying from 4 liters per minute to only 1 liter per minute. And it also can be seen from this 3D animation. So you see, when the control piston is actuated, the swash plate angle is coming from an inclined position to its vertical position. And then there is no more suction and discharging of the fluid. So that's why we have almost no flow rate when the swash plate is going to this vertical position. The third example is a lubrication system model built with hydraulic resistance library. It consists of all important components such as gear pump, bearings, oil galleries, and different kinds of pipes and tubes. The difference of this model compared to models introduced in previous slides, the focusing point is the pressure drop or losses in pipe and connections. For each single section of the oil gallery, a HR library component is used to calculate local losses as well as frictional losses. The benefit of building such detailed hydraulic network model is it's fast and easy to evaluate the losses and flow distribution at all branches by performing simulations. Moreover, it's usually impossible to instrument sensors in the circuit to measure pressure and flow rate. So with this full circuit model, one can already have reference results of pressure or flow rate at different locations of circuit. Let's have a quick look at this simulation results of the camshaft lubrication system. So you see from the camshaft bearings, we can see along this flowing direction, the pressure at cams keeps decreasing due to the pressure losses or frictional losses in the pipes and also in the T-junctions. In construction machinery, there are also various examples of system model of excavator, crane, bulldozer, etc. In this slide, we're presenting a complete excavator model created with hydraulic library, together with a simple internal combustion engine, 3D mechanical parts of its bucket, dipper, and arm. Besides, a control module is also implemented. In this model, one can analyze the excavator digging behavior to evaluate its working efficiency, fuel consumption, or even optimize the control law based on model output. Let's also look at the complete excavator model. So here we have an internal combustion engine model, which is providing torques to the pump. And then from the pump, we see the hydraulic fluid is pumping out through this valve, and then to the hydraulic jack, which is used to the movement of turret, boom, dipper, and the bucket. And here we see the 3D bodies, which are loads of this hydraulic components model. Moreover, there is also a state chart block. Basically, here inside, we design a sequence of flow chart, which is used to control the movement of the swing, for example, and also the dipper, boom, and the bucket. So basically, based on this state chart block, we can let the model finish a complete digging cycle. Now let's check the results of this bucket movement. So from this plot, you can see the trajectory of bucket movement when the excavator is performing one complete digging cycle. And you can have the simulation results such as engine speed, engine torque during the entire digging cycle, as well as this interesting and important model output, the total fuel consumption. This is also an important factor to analyze the excavator performance. Okay, that's all for introduction to different applications of hydraulic libraries.